Welcome to Pomodoro Joe for Saturday, February 4th, 2023. Today we're going to do LeetCode problem 567, permutation in string. This is a medium problem, and the problem statement's pretty short. Given two strings, S1 and S2, return true if S2 contains a permutation of S1, or false otherwise. All right, that's easy. Oh, look, I already started my Pomodoro. Nuts. All right, so that seems straightforward. Let's do it. Permutations, no problem. Start Pomodoro, 25 minutes, and get started. Now we could do this by hand, but we're Leet hackers here, so we're gonna say from itertools, import permutations. All right, now we got our permutations, and now we just have to check to see if they're in S2. So for permutation in permutations, we pass it S1 and we give it the length of the permutations we need. So that's the length of S1. And then we just say if that permutation is in S2, we return true. And if it's not in S2, we return false. Sweet, look at that clean code. Well, there's one thing we missed here. Our permutations is going to return a tuple. We have to convert that to a string. So that's pretty easy. We just use an empty string and we join. All right, look at that nice, clean, compact code. For every permutations of S1, we check to see if it's in S2. If it is, we return true, otherwise we return false. That's the problem statement. Let's see if that works. Bam, just like that. Oh, sweet. We'll submit this and then we can take the rest of the day off. 1 minute solutions for the win. Sweet. Wait, why is it taking so long? What's happening? Time limit exceed. I'm just messing with you. Yeah, so this permutations, what's happening here? Well, this permutation is going through every permutation of our S1 string. So what's the runtime? I mean, we have this nice, clean, compact code. It's only a few lines, but what's the runtime of this permutations? Unfortunately, you're thinking, oh, it's probably n squared. N squared is bad. Oh, it's so much worse. This permutations is going to be n factorial. So what does that mean? Well, so n squared, if you've got an input that's 3 characters long, like ABC, your n squared is going to be 9. Your n factorial is going to be 3 times 2 times 1. Well, that's only 6. That actually sounds better, doesn't it? We'll wait till we get to 4. So 4 squared, that's going to be 16. 4 factorial, 4 times 3 times 2 times 1. So that's going to be, let's see, 12 times 2, so that's 24. That doesn't seem so much worse than 16. 5 squared is 25, but 5 factorial. 5 times 4 times 3 times 2 times 1, that's 20 times is 120. Ooh, that's starting to look a lot worse than squared. 25 to 120. Just wait till we get to 6, 7, and 8. It goes through the roof. So yeah, so our permutations, probably not the way we're going to solve this problem. Okay, back to the drawing board. Get rid of all of this code. Wah, wah. Sad panda. All right, let's do this one for real. Permutation in string. So let's set 25 minutes on the Pomodoro timer and we will get started. All right, the first thing that we'll do is simple check. We have S1 and S2. We want to see if S1's permutation, any permutation of S1 exists in S2. Well, if the length of S1 is greater than the length of S2, that is impossible. So we'll just say if the length of S1 is greater than the length of S2, we'll return false. That one's pretty straightforward. So now the next thing we need to do, let's take a look at this. Permutations, if we actually tried to find all the permutations of S1, that is at best an n factorial algorithm. That's too slow. But we don't actually need to find all the permutations. We don't have to find the specific permutation of S1 that is in S2. We just have to find if any permutation of S1 is in S2. So is there a way to find out if any permutation exists without actually finding the permutation? There is. I like to call it the fingerprint method. So basically, we need to have something that identifies our permutations of S1 without actually finding all the permutations of S1. So what can identify the permutations of S1? Well, S1 and all its permutations have one thing in common: the set of characters and the counts. So if we create what I like to call the fingerprint of S1, that's all the characters and the count of those characters, then we just have to look for that same fingerprint in S2. And if we find it, then we can return true. If we don't find it, we return false. Okay, so we'll get started. I won't call it fingerprint in this example just because that's too long to type, but I'll call it count. So our count at 1 will be the counts of all the characters in string 1. So we'll make this an array. Let's see, there are 26 characters in the alphabet, so we can say it's 0 times 26. And we'll do the same thing for string 2. Now this one for string 2 will be a little bit different. So for string 2, we're not going to count all of the characters in the entire string. We need to just find the characters in a substring of S2. So we will create a sliding window, essentially from element 0 up to the length of S1, and then we'll slide that entire window to the right, subtracting out the counts from the previous start character and adding in the counts from the new end character as that window slides. Okay, so let's do this. Let's build up our counts. So for every character in string 1, we will need to convert that character into an index into our array. So how do we turn our character into an index? Well, we use a function called ord. Ord will take in a character and return the ASCII value of that character. Now, of course, the ASCII value of, say, the letter A is going to be 60, 70. It's going to be some big number. It's not going to be 0. So we need to convert this whole thing down to 0 to 26. How do we do that? Well, we can subtract the ord of the letter A. So if our character is A and our base is A, then this will result in a 0, giving us index 0. If our character is B, then B minus A will be 1, and that gives us an index of 1. Now, to save us a little bit of time, we can actually cache out our ord of A. So now that we have our base all cached, we can just subtract the base. And then we can say our count at index I plus equals 1. That's our fingerprint for string 1. Now we need to build up our sliding window for string 2. So we'll have a start index, and we'll set it to 0. And we'll have an end index, and we'll set that to 0. And we'll build up our initial set of counts for the initial window first. So while our end index is less than the length of S1, we'll do something similar to what we did up here. We'll get our character, which will be S2 at end index. And then we'll just increment our count for that character in our count 2. And then, of course, because this is a while loop, we need to do our own update of our index. Okay, so we've built up our very first window of counts. Now we need to start sliding that window from left to right in our string 2. So now while the end index is less than our length of string 2, we'll slide the whole thing to the right. We'll have to update our counts, and we will have to check to see if those counts match the fingerprint from count 1. So we'll basically be continuing our work that we started building that first window. We will grab the character at the end index. We will increment our count on S2. Now we will check to see if that count matches count 1. So if our count 2 matches count 1, we've found a match and we can return true. Now if we don't find a match, we need to increment our start index, but before we do, we need to remove the count, essentially remove that character at the start index from our counts. So I'll call it start character. Okay, so we get the index for our start character, and now we will remove a count from that start character, and then we can increment our start index. Finally, if we make it through all of that and we didn't find a match, we will return false. So one thing to be careful here is we've got to check our indices. So we were going for the end index is less than our length of S1, but we still added 1 to our end index before failing this, which means that when we start here, we've already added 1 to the end index, which means we probably only want to go through this to S minus 1. That way, when we start this new loop, we will actually be starting at the next end index, which completes our window. Then we can do the comparison, and then we will actually have to not just increment our start index, we will have to increment our end index as well. So the indices can be a little bit tricky on this one. It's worth maybe drawing this out on some paper. All right, let's give this a shot. Okay, that works. Let's submit that. And we pass. And we do pretty well. Taking a look at our runtime, we beat 94% of other algorithms for runtime, and we beat 28% for memory. That's not too shabby. All right, I am out of time. I'm going to leave it here. Hope you had fun. Hope you learned something. Hope you can check this one out. Again, this is LeetCode problem 567. Try it on your own, and please write better code than I do.